discussion. Last tutorial was about bone plots. We were given two simple transfer functions, and then we were asked to construct the bone plots. It was a taste of what we are going to do this week. And this week we are going to have a systematic study on these bone plots, how to generate bone plots, how to use a bone plot to build our transfer functions. Last week we actually discussed about the idea of expressing a transfer function into a product of some simple transfer functions. All these transfer functions, G1, G2, G3, and so forth, are basic components. We were saying that, say that G1 could be equal to K. When all these are normalized, that means actually all the transfer function of these basic factors, we have 1 in the constant. So you pull up, if this is not constant, say 5, you need to move, pull this 5 out, and then so you have a non-1 here, and then you get something here. This one will be combined into the overall gain. Alright, so this is the overall gain, and this one, say, for example, it's equal to 1 over s to the power n, and n could be 0, could be 1, could be 2, that determines the type of the system, right? And then n is the type of the system. And then this one could be like this one, tau 1 s plus 1. So these are normalized, first order. And of course, when this guy appears in the numerator, then it will appear like this. Then we have a repeated one, we have a second order one. So for each of these, we discuss they are bone plots. This one is basically, it's a gain plot is a constant. So the value is 20 log base 10 of k. Horizontal is this, and then this 1, this is 1. And of course, this is in the unit of decibel in dB. So the value of this one is function of k. When you have k to be 1, that means the real gain is 1. 20 log base 10 of 1 is 0 decibel. Alright? When k is 10, the log 10 of 10 is 1. So this 20 log of 10 is 20 decibel, and so forth. And of course, for the phase, this guy is for the phase, and then this guy is 0 degree, or for all frequencies, because the constant contribute no phase. Alright. So for this one, we see that when n is 1, for n is 0, nothing to discuss. Okay? And then the 1 over 1 is just like a gain to be 1. So when n is 1, then what we were saying is that this guy will pass through 0 decibel at the frequency 1 radians per second. And then the 1 decade later, say 0.1, it's a 20 decibel, 20, and then so it's like this. So in 1 decade, it will reduce by 20 decibels. So this guy is called the slope of 20 dB per decade. Right? And of course, 1 decade later, at 10, and this is this value, we know that it will be met minus 20 dB. That's called the slope of minus 20 dB per decade. And then the phase is also rather straightforward. And this is, say, the G2. This one is minus 90 degrees. Minus 90 degrees. Okay. Why? Because 1 over s gives you 1 over j omega. Right? And then give you 1 over j. And then here is times 1 over omega. J is 90 degrees. 1 over j is a negative j. So you get minus 90. So this guy gives you minus 90 degrees. And this one do not give you, this guy gives you this. Okay? So the phase of this guy is minus 90 degrees for all frequencies. Okay? And then for this guy, you can do we say that it will be equal to this guy. First, we need to find the corner frequency. Corner frequency is 1 over tau 1. We find this 1 over tau 1. This is called the corner frequency. And then on the left, it's 0 dB. On the right-hand side, it's a slope of minus 20 dB per decade. It goes down like this. This can be proven. Okay, this one can be proven. If you look at the magnitude of this guy, 3j omega. This one is 1 over square root 1 plus omega squared. Tau also. I forgot about the tau one. One over square root 1 plus tau 1 omega square. Okay, so this is a magnitude plot. And then you can see that here is the corner frequency. At this frequency, the product omega times omega 1 is 1. Correct? It's a 1. So at this frequency, this product is 1. When the frequency is much smaller than this corner frequency, and then this one is close to 0, very small. And so you can say that this one is going to be 0 dB, where this tau 1 omega is going to 0 for low frequencies. Okay? And then it's going to be when omega is much larger than this 1 over omega 1, then this one will be much larger than 1. So if you ignore the 1, so you get 1 over tau 1 omega. So it's going to be approximated by this 1 over tau when this omega goes to infinity. So basically it becomes 2 asymptotes. Right? You can argue that it's going to be approximated by 2 asymptotes. At this point, when this is 1, actually it's 1 over square root 2. Right? So the actual one is not 1 because 0 dB is 1. Right? And then it's minus 3 decibel. The true value when this omega equal to 1 over this one. So it's 3 dB. It's here. So the true O plot is this. The worst, the approximation, we say that asymptote is only approximation. The worst point is at this corner frequency. It's different by 3 decibels. Okay, others are just getting closer and closer. For the phase plot, we last time we were saying that we use a table. We use a table, and then you can actually 0 degree. And then it will start from 0 to minus 90. This is minus 90 degrees. When you use the table, you will find this is the one. At this 1 over tau, this is minus 45 degrees. Okay. This can be proven also using these frequency response. You can show this is the case, using the same idea of these approximations. Okay. So these are basically what we are saying is, for the basic factors, we have the standard O plot. Now when we have a complex transfunction, which is a product of many of such, and actually we want to get the overall O plot, and we will take this guy, right? 20 log base 10 of this guy, which will be equal to the sum of 20 log 10 of each. So the multiplication becomes a summation, as we mentioned. And then becomes a summation. Then in the both plot, then we just look at each point, each frequency, you add up all the contributions. And so that's what we discussed last time. And so here is an example. Now we are given a transfunction like this. The first thing you notice, this guy is not in standard form, not in normalized form, because this is not 1, this is not 1, this is not 1. So the K we refer there is not 2000. So you have to pull the 0.2 out. You have to pull the 10 out. You have to pull the 50 out. Then you get this new expression. So this is called a normalized transfunction. So all these constant will be 1. Then you can see the coefficient. Here, the K is 2 ohmic. Okay? K is 2 ohmic. So in this case, then the K is 2. Then we have the first order basic factor in the numerator, and then the 1 over S, and then the 1 basic factor, another basic factor. So we have, if you count the 2 as 1, then the 1, 2, 3, 4, 5. 5 basic factors. Okay? So 5 basic factors, then we are going to have this guy, and repetition of this guy 3 times. I mean, 3 times, to be precise, 2 times of this. 1 is on in the numerator. So when we have a 5, then what do we do? Which one comes first? Which one we consider first? We rank them by the ascending order of this corner frequency value. So the corner frequency value, as we said, is 1 over tau. So the 2 does not have. It's a straight line. Okay? And 1 over S, also, I mean, this is always like this. So we put it just after this constant. When you combine these two, that's fine. And very often people combine these two. And actually it might be easiest for the beginner. You separate this. 2 is 2, 1 over s is 1 over s. Okay? Then the other three, you will look at the corner frequencies. The one in the numerator has a corner frequency of 0.5. And then the one in the denominator, 10 and 50. So we rank them, we arrange this in the ascending order of these corner frequencies. Okay? Then we can generate the both plots using this. And then the phase plot, we say that we simply write out this phase formula. And then the first one gives us minus 90 degrees. This guy gives us this. Now it's a plus because it comes from the numerator. So plus arctangent of this guy. And then this one comes from the denominator. We put a minus. This contribution comes from denominator. We put a minus. Then these are standard formulas. Okay? So with this, we can construct a table. Here you see it's using MATLAB. We don't do this, and we only one. I brought over here. Okay. So actually, for 5 basic factors, we have. Let me draw a big one. So this is 0 dB, and this is omega, and this is overall full plot. This is what we want to achieve. And then the first thing we do is we want to plot the individual ones, right? At the beginning, we want to. The first one is the contribution of 20 log base 10 of k, which is 2. So it's a small value. Okay? And then the other one is let me use this one, and then we mark this. Now when you are given a blank semi-log paper, you need to mark all this. You cannot start from 0. You better start from 0.1 or 0.01 or 1 or 2, 1 or 10 or 100. So where do we start? We need to cover all the corner frequencies. So the first corner frequency will be 0.5, which is somewhere here. So we must start from 0.1 or 0.01. Otherwise, you cannot cover this corner frequency, right? So this is 0.05. And then the 1, and then 10, and then 100, and this is 1,000. So once we have this, and then this is we can say that this is 20 log G1 in my way. I call this as G1. And then the second one is passing the 0 dB at this. And then we have 20, 40, and 60. 20 decibel, 40 decibel, and this is 60 decibel. So the second one is passing this. So this one is 20 log of G2, okay, which is equal to 20 log base 10 of 1 over j omega. Okay. So you will pass through 0 decibel at this one. So this guy will have a minus 20 dB protected. slow. To draw this one is quite easy. Here's a 0, here's a 20 decibel. So you're passing through these 2 points, and you get the slope correct. And then the next one is a 25. 25 is here, then this is a corner frequency, right? And then on the left is a 0, on the right is this, same slope. So I will just use convenience, and they're using the same slope. Okay. Now we have, I also want to call this one as 20 log 10 of the G3. That one. Sorry, it's incorrect. The G3 is 0. It's going up. It's going up. It's not. So at this, it's a 0. It's going up at the rate of plus 20 dB. 20. Protected. Okay. So this is the 20 log of G3. And then the next corner frequency is where? Is at 10. So 10 and 50. Right? Gives you 50. So the G4 gives you 1/10. This 10 is a corner frequency. So on the left it gives you 0. On the right it will give a slope of minus 20 dB. And then this guy is, let me make it simple, G4. Okay. And then the next one is this. This is G5. This is G5. Full block of the G5. So individually, it goes like this, right? Then we say that the overall is the sum of this. Then we start from the left. We construct the, I use black color to denote the overall. It starts from the left before the first corner frequency. So the left, we have the 2 contributions only, because all others give you 0. And only this 20 log 10 of K and this one. So this one add to this one, basically you shift this one up by this much. Okay. So on the left, you get this. So this one is 20 log of G1 times G2. Sum of this, pull up. Okay? You get this one, and then this one will come all the way until you hit the first corner frequency. At this new corner frequency, then you have the new contribution. So the original is a minus 20 dB protected. Now after this gives you plus 20 dB protected. Then they add up to 0 dB protected. So flat. Alright? So you bend it upwards and then you get 0 dB protected. This will continue all the way to this 10, where you get a new contribution. Because before this, we have only 3 contributions. So that's what you get. So at this 10, you get a new contribution, minus 20 dB per decade. So you add to this 0, and then you bend downwards. Then it will continue until you hit the next corner frequency at 50. This guy will give you another one. So this one will bend it even further. So this is minus 20 dB per decade. And then this one is actually minus 40 dB per decade. So this will continue all the way. So this one is the sum of all these individuals. Okay. So this is overall. We say that this is a 20 log 10 of G. So this is the overall plot. And from here, from my drawing, you can see the reason why we want to rank all these basic factors based on their these corner frequencies in the ascending order. Because if we look at those, the contribution one by one, and then from the smallest to the bigger ones. Okay. So this is what you get if you use a MATLAB. You get a red color one. The black one is what I get from there. Okay. And then this phase plot is by using the table. And then we know that once you have identified all the corner frequencies, 0.5, 10, and 50, then you need to use a range to cover all this, right? So when you construct this table, then you use the frequency, this range, to cover all the frequencies. And then the 0.1, and 10, and 0.5, 10, 50, and somewhere like this one, larger than that. In between, actually, it doesn't matter too much. Then you plug into the formula we have shown, then you get a sequence of points, then connect them by single square. That's good enough. Don't use a single code for the phase. Minimum phase and non-minimum phase, they are different in the sense that for the minimum phase, you see all these basic factors in pluses, no minus. Once you see a basic factor containing minus, this is a non-minimum phase. Last week, in one of the tutorial questions, the last question, the part A, we have the -1, and then that gives us quite a bit of that require a lot of explanation on the phase, right? The phase is 180 minus arctangent something. So that is due to the fact that it's a non-minimum phase. In our study, we focus on the minimum phase. Okay? Non-minimum phase and then is not the focus of our study, but we need to know. And the other one is the time delay. Time delay is not a linear function, but it's a very special function. Time delay appears in our system very often, so we have to deal with this guy. The time delay is e to the power minus TdS, right, in the transfunction. And in second year Laplace transform, we study this one, and then in time domain, say in time domain we have a function, and in Laplace transform we get this Laplace transform, this transfunction, right? And then when the time function has a delay, a time shift like this, then the Laplace transform will give me this times e to the power minus t0s. This is how we understand. So in the time, most of our system has a time delay. Is it significant or not? So we have to deal with a time delay. Okay. So this guy comes in. This guy comes in this way. So now if we are able to draw the ball plot of this f of s, then when this time delay comes in, how is this guy affecting the ball plot? This is what we want to understand. So we look at the contribution. You treat this guy as, say, the last one. Say we did this is due to time delay. We treat this guy. Okay. And then when we draw both plots, then it's a magnitude contribution, and it has a phase contribution, right? This will contribute the magnitude as well as the phase. So we look at the magnitude, we take its norm, replace s by j omega, we get this. And then use Euler's formula, and you get this. And then the norm of this guy is 1. So what it means is this guy contributes 0 dB to our ball plot. So in the ball plot, if there is a time delay, there is a 0 dB for all frequencies. Okay? Then when we look at its phase, it has a significant contribution. Its contribution is minus TD radians per second. And then you convert it into degree, you have to use a 180 degree divided by pi. So this is in degrees. So you can see that this is a negative. That means drag down. And then when frequencies increases, this is going to be very, very negative value. So if we draw the phase of this guy, here d, if we treat this one as a basic factor, e to the power minus TTS, and its frequency response is called JTD omega. So it's a magnitude of this guy, J omega, is equal to 1. So the beam plot is 0 for all frequencies. So it doesn't bother what we have obtained. But the angle of this guy will be equal to that value, negative TD omega times 180 over pi. So in this case is when the frequency is 0, that means to this, it has a 0 degree. Okay. Then when frequency increases, going to infinity, it's going to be like this. So it's going to minus infinity. So the damaging is very bad. As we're going to see later on, this guy is going to go all the way to negative infinity. So when a system has a large time delay, then it's not going to stable. There's no way you can make it stable. Then we look at the some characteristic of this ball plots. You look at this overall transfunction, you can rewrite it in this way. For lower frequencies, all these will be relatively small to 1. You drop them, so you get the approximation as a k over as n. As I mentioned over here, and then on the left portion, when left portion means frequency is small. So the whole plot is basically approximated by the constant and the 1 over s. But here, if s is not, if n is more than 1, then you get the, the n could be 0, n could be 0, could be 1, could be 2. Okay. So that's the characteristic of whole plot. So if n is 0, the left portion is flat. It's a flat because it's only a constant, so it's flat. So we stop here does not mean that there's no value on this side. This value will continue all the way the left portion or the low frequency. So for when the n is 1, then we have this. That's what we have over there. When n is 1, then you have one single integrator. And then we can see that how to compute some specific points. When omega is 1, 20 log of 1 here, k is the original. So it will be equal to the 20 log k. So at the here at frequency 1, okay. This is omega equal to 1. At this frequency 1, then this value is 20 log k. Okay. The other case is when this ratio is equal to 1. This ratio equal to 1, then the whole thing is equal to 0 decibel. Correct? So that means at 0 decibel, this value is such that this ratio is equal to 1. This is equal to 1, that means actually this crossing frequency is equal to the value k. So what is important of this one is when the left side is a type 1 system, then you simply look at its left portion, it cuts with the 0 decibel. This value, omega, is the k value. You can identify the k value from this both plot. When it's, if there's a corner frequency before this hitting the 0 decibel, such as this bend it here or bend it up, then you just extend the left portion until you hit the 0 decibel. And then this value will be called omega 1, that is a k value. So the k value here. So this one is very easy to identify. And when when n is equal to 2, then when equal to 2, then you can go over the same reasoning. I don't want to go into details. And basically, at frequency 1, then you have this 20 log of k. So at frequency 1, the red color here, this value is 20 log of k, no change. But when you extend the left portion and cut here, it's not going to be the k value, but it's related to the k value. So you cut this frequency at 0 dB, you read it out, it's actually related to the k value by square root. So k is equal to omega a squared. So you get this frequency and square it, and then you get the k value. So this also helps us to identify the gain value of the transfer function. In particular, later on when we do the model. Now, when we discuss so much, what is it? I mean, we can construct a ball plot. Now we understand how the ball plot is constructed. When we are given a ball plot, are we able to derive the transfer function? Now, in the first 7 weeks, also taught you how to build the model for a motor with a load, without load, and some other systems, right? But that is based on the first principle. That means the physics, Newton's law, and so forth. Now, if you don't have, then you buy a product, and then you don't know what is inside, and then you get that thing, and what are you going to do? What you are going to do is you are going to build, design a test. And here is the given transfer function. And then what you do is you feed in the sinusoidal functions, A in omega t. You feed in this one, and the output you are going to get the AO sine function, same frequency, and with output phi. Right? And this will give you the overall when you change the frequency. I mean, these give you the ratio. And then the phi, the angle here, will be equal to the phi 0 minus this one. If this is 0, then it will be simply the phase of the output. So you get all this, you plot them in a similar paper. In one frequency, you get one magnitude. On the phase, you get the same thing. I mean, you get another point. Then you change the frequency of the input signal, then you are going to get many values. So you are going to get this ball plots. Correct? So once you have the ball plots by experiment, then the question is, are we able to derive the transfer function? So this is the ball plot. The continuous one is the ball plot we obtain, and that is the real thing. And then from this, are we able to derive a transfer function? Now, once we understand how the ball plot is coming from, then we are able to. The first thing we do is we plot this one, the ball plot on this similar paper, and then at the corner we construct the slope. This is minus 40, minus 60, 1 decade. So this line has a slope of minus 20 dB per decade. And then here, minus 20, minus 60, and then this line has a slope of minus 40 dB per decade. All right? So we try to use this one to fit, you move the parallel to fit into this. So if this, we are able to fit the minus 20 dB per decade, that means that this is due to a second order system. If we use a minus 40 and shift, and then we get a minus 4, we can fit in a minus 40 dB per decade, that means that this is a second order system. Second order system. And then if you have a 0 here, flat one, that means you have the left portion. You have a flat one, that means n 1 over Sn. This n will be equal to 0 if this is the left portion. Give you the flat one. So basically you fit in the 0, minus 40, minus 20, then you know the corner frequency. you know this corner frequency. Because from the construction, we know that at corner frequencies, we get new contributions, which will bend the bulb plot up or down by the multiple of minus 20 dB per decade or plus 20 dB per decade. Okay? So these are the information we get. So from here, this is left portion, we know that n is equal to 0, so that is due to a constant k. Then is a constant k will be, you read this out, 20 decibel, so 20 log of k is equal to 20. 20 is from here. So from there, we can get k is equal to 10. And then at the next corner frequency, at this corner frequency, 6, no, this is 10, at 10. This is a corner frequency at 10 or 9, it doesn't matter where you read it. Okay? Suppose you read it as a 10, and then here the slope changes from 0 to minus 40, means what? Here there is a second order system. Okay? Because each single one gives you a band of minus 20. You have 2 of them here, then it's going to be minus 40 change. So here we assume that there is a double, single basic factor. So we say that, okay, and then here we have 2 basic factor with a corner frequency at 10, okay, with a corner frequency at 10. So we have 2 of them. Because one gives us minus 20 dB per decade. 2 of them will give us minus 40 dB in total. Then from the bulb plot at 100 radians per second, one hundred radians per second. Here we see that the slope change from minus 40 to minus 20. So the net change here is plus 20 dB per decade. Correct? Plus net change is plus 20 dB per decade. So why is that? That is due to a basic factor at the 0. So this is what we can conclude. We can conclude that, oh, there is a basic factor in the numerator with a corner frequency at 100, so the tau is 0.01. And then you put all these together, and you will get the transfunction. And this is the transfunction we derive from the measurements. Okay? When we are given a system without transfunction, then we carry out the experiment, we get the bulb plots, and from the bulb plot we use the knowledge how the bulb plot is coming, and then we can derive where are the corner frequencies and how many contributions we have. Alright, so it's a bit long, but those are foundations. Once you have a good understanding of the foundations, then solving all these will be rather straightforward. So in this case, then probably I'll skip some of this or point out the key things you need to know. Then I'll leave it to you for this guy, A. The first thing you spot is this is not normalized. You need to normalize by pulling this 10 out, then this gain will become 10, right? And here you have 1 over 10. And then there's a 10 here, there's a corner frequency 1, and then there is a corner frequency 10, so only 3 basic factors. And for the second one, then also first thing you notice is this is not in normalized form. You pull the 20 out, so this becomes 50. You pull the 20 out, this will become 2.5 or something. Right? So you need to convert into the standard normalized form, and then it will be rather straightforward. Okay. So once you normalize it, and then you identify 3 basic factors, and they are at 1 and at 0, at 10 radians per second, and the phase angle, you can write it out and construct the table for the phase. Then you can construct a whole plot easily. Before the first, we have a 2 corner frequency. One is at 1, the other is 10. All right? These are the 2 corner frequencies. We need to include in this frequency range we select. And at best, we have 1 decade below the first corner frequency. And now we start from 20 decibel because the K is 10. K is 10, then so the constant is 20 decibel. It will go all the way until you hit the first corner frequency at 1. It's a 0, so you bend upwards at the slope of 20 dB per decade, and then there is a 0, which will bend the slope downwards by minus 20 dB. And phase plot is just follow the table. Okay? So for the part B, this is a given function. It's not normalized, so we have to normalize it. Okay, we have to normalize it. And then when we do the normalization, we pull these 2 out, we pull the 20 out so that the gain above changes. So in this case, we identify 3 basic factors, 2.5, that is 8 decibel. And then the first order was the corner frequency at 0.5, 1 over this, right? That is a pole. Another one is at this, which is 20 radians per second. And then the phase, we can write down the formula and then generate the table. So with these 3, then we do the same. You can see that this is a bow plot. We start from the left, lower frequency, where you have fewest contribution. Only the 8 decibel will give you the contribution. The other do not come in yet. The other give you 0. Okay? So 8 decibel, all the way it will go to it will hit the 2 radians per second. That is the first corner frequency. Over there we have 1 contribution from the top denominator. So it bends downwards by 20 decibels. Now this is a bit tricky, huh? Look up here. So from this 20 to, how to draw this minus 20 dB per decade? One way is 20 to 2 to 20. This is 1 decade change. So this 8 and this must be corresponding minus 20. Okay, it's very complicated, very easy to make mistake. So the good way is you have 1 decade, and here you have 20 decibel. Then you draw a line, you use this one as a reference, and then you shift this in parallel, and then connect to this point. So this line will have minus 20 dB per decade, or anywhere. You just shift this one up and connect with this point. Okay, it's a good way to do it. And then do the same thing, and then you use minus 40 dB per decade. This is minus 20, this is minus 40. So this is you draw a line here, this is minus 40, and then shift in parallel. And you can get this line. Okay. For part C, we get a very complex function like this one. And both the numerator and denominator have a second order polynomial. So what we have to do is, but both of them are omega n, okay? So the constant is not 1, so we need to normalize it. You pull the omega n squared out, you pull the omega n squared up, then you get this. So when all these are 1, then we have a normalized one. Okay, you can see that this guy, the k is 1. K is 1, that means on the left, it's a 0 decibel. Start with a 0 decibel. And then this second order system, we didn't discuss it here, but the second order system is a standard one we know. At the omega n, then it will be like this. This is 0 dB. And this is minus 40 dB per decade. And then here is a value here. I think it's 20 log 1 over damping ratio or 2 damping ratio, I forgot. So I think you need to check that. Right. One is a one damping ratio, just one here. So this one is related to the damping ratio. When this one is 1, then it's 0. That means you don't have a peak here. But when this is small, 20 log of a big number, it's going to have a very big value. Okay? So in this case, we have two. If you draw this factor 1 in the numerator and then factor 2 in the denominator, so you separate this as a G1 here, this is G2. You can have 2 basic factors. This guy gives you this. In the numerator, and then it has a corner frequency of omega, and then this is going up at the rate of 40 dB per decade. Here, the difference is 20 log damping ratio, which is negative 14 dB. And then here, this guy is what we have shown here, but the damping ratio is a rather, it's a given. Damping ratio is 0.6. So the damping ratio is 0.6. This peak is actually reduced. When it's 1, it's 0, right? And then when it's 0.6, actually it's already 0. Below 0.7, it's 0. Or below But basically, we get this symmetric in a sense at the same corner frequency, but one is this way, the other is going down this way. So when you add these two together, before this corner frequency, 0 plus 0, okay? And then for larger frequency, plus 40, minus 40, you also get 0. Only during this there is a dip. Here there is no peak. When you add this portion and to this portion, then you're going to see a dip. You see a dip here. So when you add them up, then the overall gain plot will have a dip here. So we call this as a notch filter. Basically, for the low frequency signal, high frequency signal, the gain is basically 1. So this will allow the signal to pass through. And then at this range, at 10 radians per second, the signal will be filtered out substantially. Minus 15 is 0.2 or something like that. And for the phase, you add them together and then that will be. But in this particular case, what is important is the magnitude. Okay. So, any questions so far? So for 9.2, we are given a boat plot, and with the 3 transfunctions, we are asked to find out which transfunction is the best fit for this given plot, right? Then you look at this boat plot, you can see that, okay, from the left side, you can see the feature. In 1 decade, it reduced by 20 decibels, from 40 to 20. Okay? So it's the n is equal. It has this guy, 1 over s to the power n is equal to 1. This is the first confirmation. We also have 2 corner frequencies. One is at 10, the other is, what is this? It's 10, 20, 30, 40, 50. So another corner frequency at 50 radians per second. One at 10, one is at 50. So you count 10, 20, 30, 40, 50. So you get 2 corner frequencies. At this 10, it's a bend upwards. That means this is due to a 0. Something from the numerator, right? And then here, at this 50 radius, at this corner frequency, the slope bend downwards from 0 to this. This means in this 1 decade, it reduced by 20 decibels. This is about 20 and this is 0. So this is minus 20 dB per decade. What does this mean? That's first order basic factor in the denominator. So by looking at this, we can know roughly. Then you can see this is not possible. Right? The first one is ruled out because it does not have this guy. So the first one crossed out. Then the second one is 1 over s, 1 over s, both are possible. Then you look at this one has 0 at 10, 0 at 10. This guy also has a 0 at 10. This guy has a pole at 50, and this guy has a pole at 50. So by looking at the pole and zeros, poles are okay. Right? Now the only difference is the gain. So how to identify the gain? You pull out this, you pull out this. You need to normalize it, right? You normalize it, and then what do you get here? 1,000 divided by 50. And then this one is 500 divided by 50. So you have two different gains. And the gain is associated with the left portion. We identify. So this is first, so you extend this one all the way to cut the corner 0 dB, and we know that this will be the K. So if you extend this 20 and then you extend, it will be at this 100. If you continue to extend, this is minus 20 dB per decade, and then from here to here, reduce it by another 20. So that means the K is 100. K is 100, which one gives you 100? This one, right? So you know this is the correct transfunction for this one. When we know how to construct the whole plots, and actually when we are given the transfunction, we can have the reverse process. Okay, for 9.3, we are given this bow plot. This is 0.01, this is 0.1, and this is 1 radians per second. Vertically, it's 0 dB, 5, 10, 15, 20. Okay. On the lower frequency, you can see it's a flat 20 decibel. That means K is 10, right? On the right, you can see that 1 decade, it changes about 20 decibels. From here, you feed the slope minus 20 dB per decade. So this one is about, should be a first order system. I mean, first order basic factor in the denominator. Okay. So where is the corner frequency? We need to find out. And find the gain and the time constant. So we need to find the gain has been identified already, as I mentioned. So for the previous, you might want to, if you like, you can take the photo I was discussing verbally. So for this, one, then we feed in the asymptote. We feed in the asymptote on the left, 0 dB. We read this K, there is a 20 decibel. We can find the K to be 20. And we can find the K to be 10. On the right, we fill in the straight line of a slope minus 20 dB per decade. We find the intersections here. That means that these are corner frequency. Corner frequency is at 0.1. That means 1 over T is 0.1 or T is 10. So in this case, this first order transfunction with the two parameters have been identified. Right? So with this knowledge of the whole plot, we can identify the parameters of the transfunction. We are given a minimum phase, we are given a magnitude plot, and then we're saying that this guy is a minimum phase system. Okay, that means when we derive the transfunction, we put process. We don't use minus. That's all. So determine the approximate mathematical model in the form of transfunction. So given this guy, we want to derive a transfunction. How to do this? First, we understand the idea. How this whole plot is constructed, right? Like that. So we try to fit in the straight line of a fixed slope. On the left, you can see it's basically flat. We use 0 dB per decade. We fit in here, we read the this value. Then we use this value to figure out the K. Then for the right, we fill in a straight line, and actually this one is has about 40 dB per decade, negative 40 dB per decade. So we use that slope and shift to fit in. Now, when you do the fitting, one trick, when you do it yourself, you might face a problem. You are not able to fit every section. Every section you cannot fit perfectly. So where do you fit? You normally use the higher end. For the lower, you use the lower end. Okay? And because these are in between, they are not accurate in the sense they are affected by the turnings. Okay. So you start from here, here. Then by observing this, then you fill in this one, minus 20 dB per decade. Now this one is a typical problem, as I mentioned. When you try to fill in the line, you might want to fill in like this. Right? No, cannot do this. Even though you fit, you get a very good fit, which is not a multiple of a minus 20 dB per decade. There is not the fixed slope. We need lines of minus 20, minus 40, and so forth. So even if you don't get the perfect fit, then you must stick to that slope, minus 20 dB per decade. And here you can see that it's turning like this, so it looks like a flat. So we use this horizontal one to fit in. Okay. And you can see that, in that case, here what happened? If you have 0 here, you turn to minus 40. Actually, this is a second order system. Second order system, that means you have a hump, like this. So it fits into our expectation. Second order system here. So it makes sense. So what you do is, now you have the corner frequency. You have the net change in the slope. Then you can fit in the basic factors. Okay. Now here is on the left portion, you read it out as a 14, you read it out as a 15, 16, it doesn't matter. Okay? What care most is you get this right. This formula, you get it right. The reading might not be perfect, it's okay. Alright, and then from 0 to minus 40, minus 20, so we expect that one basic factor in the denominator. Okay. And here there is a change of a net plus 20 dB per decade. We expect this to be from the numerator. So the corner frequency, you read it as a 9 or 10 or 8, it doesn't matter to me. So that is less critical. What I care is this need to be minus 20 dB per decade. If you don't use that, you think you fit perfectly, that is not right. Okay? So here is another corner frequency, and here is a 6 decibel. These are two damping ratio, these are not this. Okay. So using this formula, you can get the damping ratio, and from here you can see that there is a second order system. Okay. So once you identify all the corner frequencies and the gains, and you know where they are coming from, either the numerator or the denominator, and you put them together. Here is the transfer function. We say the approximate. So any questions? Okay. If we know that, we move on. So 5, we given the transfer function in this form, but we don't know the parameter n, k, a, damping ratio, and natural frequency. We don't know all this. So we are given this. Okay. So from here, we need to identify all these parameters. This is more challenging than the previous one, because the last one we draw the asymptote for you, and here you have to fit the straight line yourself. Now, fitting the straight line yourself can lead to multiple answers. Okay? So the question, the answer in the given there is only a reference. Okay. Now, as I said, given this guy, and then you want to fit in the lines, the asymptote with a fixed slope, 0, minus 20 dB per decade, minus 40, minus 60, and so forth. So the first thing you want to look at is the left portion. 1 decade, you see how much change. This around 50, this around 30. So you can see that this is a minus 20 dB per decade. So you draw a line, minus 20 dB per decade, and fit in. Okay? And then on this side, you can see that the last decade, and here is minus 85 already. But here is about 20. So minus 20, minus 80, there is about 60. That's the change in 1 decade. So this is minus 60 dB per decade. So minus 60 dB per decade, that is this much. You draw a line here from this point to this point, and you shift in interval to fit in. So the left portion and the right portion, you fit it in already. Okay. Then you can see that some information are given. Like at 0.5, there is a pole. That means that at 0.5, this is 0.1, right? 0.5 is here. There is a bend downwards. That is due to this guy. Okay? And then there is here there is a second order system, and it's near here because this hump is should be due to the second order system. And then there is a zero. Then you can see that the zero will make the slope gentler. So you can see that around here it's going down, but it suddenly changed. I mean, you can see that it's bending up, gentler. So you can expect that the corner frequency will be somewhere here, but we don't know yet. Okay? Of course, this guy is not in normalized form. So the K is not the K we have been talking about. So we need to combine all this A and 0.5 omega n squared. You normalize it, then you are going to get the new K. Okay? That will, you can derive that K from when you extend this one to all the way to intersect this is 0. Okay, you can get the K value. That will be equal to the lump of this Ka divided by 0.5 and divided by this omega n squared. So what we do is, as I mentioned, and we draw three reference lines. They have minus 20, minus 40, minus 60. And then we use this one, and then we see it bend it down, and then you use this one to fit in, and so forth. Now here there's no unique solutions. Different people have the different answers. Okay. It's all right. So long these lines fit in the correct order as we did the analysis, we have some hint on the structure of the transfunction, and some corner frequencies are already given. Okay. So we get these red lines, and these red lines have intersections. These intersections will give us the corner frequencies. And we start with the K. These go all the way intersect to these 4. That means that K is equal to 4. Now this, I will say that K A equal to 4. When you do this is the overall gain. When you do the normalizations, actually the transfunction will have K and then times A, and then divided by 0.5, and then divided by omega n squared. This should be in front, right? We do the normalization. We know that intersection is equal to this. That means that 20 log base 10 of this guy, Ka 0.5 omega n squared equal to 4. So now how to figure out this? Then later on from corner frequency we figure out this one. From corner frequency we figure out this one. Then the only unknown will be identified as a result. Okay? So this is the calculation. We say that n is 1, and then at this first corner frequency, it changed the gradient of asymptote from minus 40 to minus 20. So there will be a 0. That means this is a corner frequency, right? So A is equal to 2. At A, there is a resonance. That means omega is a second order system. This resonance, omega n, is equal to 8. And then from the reading of the plot, which is also estimate, we get this 8 here. You can read that from this asymptote to this value. Now at this intersection, so this value is about 8. You read as 10 or 7 or 6, it doesn't matter. So what is important? You use this formula correctly, and then you can get the definition. And this is what I mentioned earlier. And after normalization, you get a new k, which corresponding to the intersection 4. And now the A omega n has been identified already. So from there, we can compute the k to be 64. Okay, any questions? So do your homework, please. Remember before and after. And next week you are going to have the quiz, and then you need to do your homework. And all the quizzes will help you to lay a good foundation, because it's 40% in total. So in final, you don't count on the final result. Okay, if no questions, that's all for today.